Hi everybody. So I wanted to go over some of the final parts of your notes that we went over on 9.3 continuity. So I'm going to go ahead and jump into it. And the first question was whether these four functions were continuous. So we'll start from the top. 3x to the fifth, or to the second, minus 5x plus 8. If you think about that, we know this graph is going to be quadratic, and we kind of talked about in class, any quadratic or any polynomial function for that matter, you can draw without lifting up your pencil. Therefore, it's continuous on all parts. And, the other idea is, can I substitute x anywhere, and do I have any problems that arise when I substitute x? There's no problem substituting negatives. There's no problem substituting positives. Therefore, the domain will be all real numbers. Let me get a different marker here. I know you'll tell me not to use red, so I'm going to use green here. Negative infinity to positive infinity. Those are the possible values, or the domain of x. So moving on to the next one with that same idea, we ask ourselves, here we have a rational, it's fractional, rational, like I mentioned in class. What numbers can x not take on? I think you might remember one of the key points in the class was you cannot divide by 0. In this case, what would give division by 0 if x was 3? So x cannot be 3. Also, x cannot be negative 1. Because if it's negative 1 plus 1, that'll be division by 0. So basically that's the domain, but how do we write this in what we call interval notation? So we're going to do all numbers from negative infinity to negative 1. And then we do this union. All the numbers between negative 1 and 3. And then all the numbers after 3, which is 3 to infinity. And this is how you write that. So this is just kind of a fancy way of saying all the numbers before negative 1, all the numbers between negative 1 and 3, all the numbers after 3 to infinity. It's just another way of saying not 3 and not negative 1. So that's all we have there. I think I'm going to do the fourth one first to kind of emphasize a point. Oh, actually, I did want to say this. You can always kind of check your work, right? You have graphing calculators, but if you remember from class, this would be a vertical asymptote at 3, and there's going to be another vertical asymptote at negative 1. And if you put it in your calculator, and also actually from class, the degree on the bottom here, if you multiply this out, would be x squared, and the top would be 1. So that's the case where you have a horizontal asymptote of y equals 0. Then you can plot some points with or without a calculator, but you'll get something like this in your graph. Okay. So, in other words, you'll see that x, there's an asymptote, x cannot be 3, x cannot be negative, and verifying this domain. Now for the square root of x plus 1, on all square root functions, so on fractional functions you look to see what makes the denominator 0. On square root functions, you cannot take the square root of a negative number. Those would be imaginary numbers. So the way you start off for domain questions on square roots is that you should write what's inside the square root, and you should know that inside the square root has to be greater than or equal to 0 because we cannot take the square root of a negative number. And basically the domain will just be the solution to this inequality. So I solve it because I know the inside has to be greater than or equal to 0, so I'm going to subtract 1, and basically that's my domain. Okay, but how am I going to write this? So in order to write this, you're going to have to do interval notation from x is going to be greater than negative 1. So I'm going to greater than or equal to negative 1. I'm actually adjust my symbol here. It shouldn't be an open parentheses, but rather I should put a bracket because it can be negative 1. Because if I put negative 1, you get 0. I can take the square root of 0. And you can try other numbers too. Like we can take the square root of 2 plus 1, right? The square root of 3. I don't know what it is, but we can take it. I can't take the square root of negative 2 because it's outside the domain. And that would give me the square root of -1. Try to input that in calculator, you get an error. So that's for this example. I want to go back here, and now square root and cube root. Okay, so can you take the cube root of -1? Well, it turns out you can. The cube root of -1 is asking what times itself 3 times will give you -1. The cube root of -1 was actually -1. So actually negatives, there's no problem with negatives here. Okay, so you can take the cube root of negative numbers all you want. So then we ask ourselves the original question, is there any restrictions on x? Well, if we can do negatives, then basically this can be whatever it wants as well. So, because I could take the cube root of negative numbers. So in this case, I would say if it could be whatever it wants, it's negative infinity to infinity. Now, okay, maybe you have some questions on that. You can also take a look at the graph, and I graphed it on the calculator. And you can see if you put -3, that's going to be 0. If you put +3, that's going to be 0. And then also if you graph 0, the cube root of 9 would be approximately 2 point something. So you get a graph something like this. Okay, which verifies the domain for x can be any number from -infinity to infinity. Okay, so that's determining whether they're continuous or not based off the definition. And if you remember the definition, actually, the definition says 3 things, so we can go back to that. The limit as x approaches some c exists, f of c exists, and both of those have to be the same. Here the limit does not exist, so that's why this is not correct. Here the limit exists everywhere, and f of c is the same as that limit everywhere. Okay, so that's why this one would be continuous. So moving on to the next and final page, we have a process for constructing what we call sign charts. And so I'm going to kind of jump into that process. So we want to find all numbers x such that f is discontinuous at x. So we know -2 would be one such number. So that's step 1. I'm going to find what we call partition points. So one of them would be -2. Okay, and I also want, so that would be like step A on that constructing sign charts procedure. So we found that that's going to be -2. That's discontinuities. Step B would be to find all such numbers where of x such that f of x equals 0. So this is considered f of x, and I want to know, when does this equal 0? To answer this question, if we think a little bit, we only need to know when the top is 0. If the top is 0, it doesn't matter what the denominator is, the whole thing is 0. So, or if you want an algebraic way, multiply both sides by x plus 2. The x plus 2 will go away, and you end up with this, and you solve that, and you'll end up with what really is an x-intercept. So if you'll recall, if you set an equation equal to 0 and you solve it, you end up with the x-intercept. But that would be part B on that procedure. So step 2 would be to plot the numbers found in step 1 on a real number line. Okay, so a number line, meaning what it sounds like, a number line. So I'm going to graph -2 and -1 on that number line. So that is done. And then step 3, select the test number in each open interval. So this has a couple of intervals. This has the interval before -2, okay, to -infinity, and it has the interval from -2 to -1, and then it has the interval from -1 to infinity. So we want to write a little table of that. So one of them is -infinity to -2, -2 to -1, and final one is -1 to infinity. And what you want to do is simply test. We're going to test some numbers in each of these intervals. So just pick some number, and you could all pick, everybody could pick different numbers, as long as they're in their intervals. So what's in negative infinity, -2, -3? What's in here? Maybe -1.5. And then what's in here? 0 is a nice number. And then what you're going to do is, again, this is f of x. I'm going to plug those in. So we're going to plug in f of -3. We'll figure out what that is. F of -1.5. We'll figure out what that is. And f of 0. We'll figure out what that is. And you can use your calculator. Feel free to do that. I'll just kind of do it here. -3 plus 1 is -2. -3 plus 2 is -1. So that's going to be -2 divided by -1, which is 2. Okay, or you can just write the answers. -1.5 is -0.5. -1.5 plus 2 is -0.5. Actually, positive 0.5. So -0.5 divided by positive 0.5 is -1. F of 0 is just going to be 1/2. So this is 1/2. And really, I don't actually care about the numbers. What I care about, whether it's going to be positive or negative, okay? So, positive, negative, that's the final result. So, obviously, that's +2, so it's positive. That's a -1, so that's negative. That's +1/2, so that's positive. So, you might be thinking, well, how does this answer the question? The question is solve the inequality, which I want to know when f of x is greater than 0. Well, in other words, when is it positive? Okay, it's positive here, positive here. We've answered the question. So the intervals, the solution would be x is positive, solving the inequality. So x would be positive on the intervals negative. Yeah, we'll just write the intervals. It's going to be greater than 0 on the intervals -infinity to -2. And yeah, I guess we can just reiterate, x plus 1 over x plus 2 is greater than 0 on the intervals -infinity to -2 and -1 to infinity. Okay. Okay, so I kind of made a mess of that. Let me change colors here. I'm just going to use black. So for the final one, or for this one, we want to do the same thing. And